Yeah, so hello. I'll start with a brief overview of what we do. So we consider the problem of sampling direct acyclic graphs from modular distributions. And what it means is that the probability weight of any DAG factorizes as this kind of product over local factors that depend on one per node, each of which depends only on the parents of the node. And the reason we consider distributions like this is that if we do Bayesian network learning using a Bayesian score, then the posterior distribution over the Bayesian network structures will be a modular distribution. And so it's a basic problem in Bayesian network learning because we want to sample from the posterior distributions. And so the contribution in our paper is mainly like combinatorial algorithmic. And the idea in the algorithm is that that we first sample the root layering of the DAG, which means the ordered partition for the DAG you get by repeatedly removing the root nodes in the graph, which means the nodes that have no parents. And after we have sampled the root layering, then we sample the DAG conditional on the root layering. And we came up with a way to pre-process the distribution in such a way that in roughly 3 to the n time, such that we can then draw samples, as many samples as we want in 2 to the n time per sample. Then there are also important special cases such as uniform sampling of DAG, which is a basic problem, and there we'll be able to improve the running time bound to n squared. And then a middle ground between these two, so the symmetric case where we only control the number of parents for each node. So it could be useful, for example, in algorithm testing or sampling from the prior, because you can control the density of the DAG, and there we get NQ preprocessing time. Okay, but now let's switch to describing our work more in detail. So the problem is described in terms of modular distribution. So we have a fixed set of nodes V, n nodes, and we look at the distribution over DAGs in V, where the probability distribution is given as this kind of unnormalized probability W, which is defined as a product of over all nodes V of a local parent set weight WV, which depends only on the parents of the node. So for example, for this DAG G, you can compute the probability weight by multiplying these 5 parent set weights. And the input to our problem is encoded as simply listing all these parent set weights. So for every node and every possible parent set, you give the weight. So of course, the input size will then be exponential in the number of nodes n. And the problem is to sample DAGs from this distribution. And this has been studied before. The previous methods are mostly based on Markov chains. The problem with those is that we don't know how long we should run the chain for to get close to the distribution. Then also this uniform case where uniform sampling DAGs has been studied. We already have a polynomial time exact sampling scheme. But in this work, we improve the running time bound. And also there are related problems such as optimizing the weight. And it's widely used in Bayesian network learning, and there are many practical approaches. But of course, the mode of the distribution doesn't tell us everything about the distribution, so that's why we want to do sampling. Another related problem is the problem of computing the normalizing constant. We're able to do this in roughly 3 to the n time. And then people have also tried to bias this distribution in a way that makes it easier to handle computationally. But yeah, so in this work we want to use the exact modular distribution and use exact algorithm for it. And we do this by combining ideas from these 2 previous works. So from Kuipers and Moffa we get the idea of using root layerings as the basis, and the way we do the computations is inspired by the inclusion-exclusion recurrences of Tian and He. So the algorithms are based on the root layering. So recall that it's the layering you get when you repeatedly find the root nodes, the nodes with no parents, in this case A and B, and remove them. Then the next layer is C, D, and E, remove them, and so on. And the reason we are interested in this is that once we have fixed the root layering, sampling the DAG from the modular distribution becomes easy. So let's say we want to sample a DAG with this root layering R here. A and B are of course roots, so they have no parents. And actually what happens is that every other node can then select their parent nodes completely independently from each other. And the only rule is that they have to select parent from the previous layers, and at least one parent from the previous layer. So, but of course in practice, we don't have a fixed root layering. The root layering could be anything. So the idea in the algorithm is to first sample the root layering from the correct distribution, and after that sample the DAG. And we already saw how to do this phase 2 in the previous slide, so we focus on this first step. So we sample the root layering using an iterative scheme. We start from the set of roots R1, then the next layer R2, and so on. So if we have sampled up to Ri-1, we sample the next set Ri, which will be a subset of the set of remaining nodes U from the conditional distribution. And actually it's independent of everything else except the previous layer Ri-1 and the set U. And this will actually factorize into 2 parts. The second part is the easy part. It simply accounts for the possible sets of parent sets for the nodes in Ri, and it can be efficiently computed using the zeta transform of these parent set weight functions. So the hard part is this F thing here, and now we'll focus on computing this. So F is defined as this kind of sum over DAGs, of the weights of the DAGs, with constraints that V minus U have to be roots, and if you look at the subgraph of G induced by U, then the set of roots has to be equal to R. So this is the same thing again. And we don't want to iterate over DAGs because there are too many of them. So if you think about what kind of DAGs we have in this summation, so we have split V into 2 parts, and we have a subset R of U, and in any DAG, the nodes in V minus U are roots, so they have no parents. Then in R, the nodes can have only parents in V minus U, because they have to be roots in U, and then we have some other DAG with the only constraint that all the nodes have to have at least one parent in U, because otherwise they would be additional roots. So we want to sum over DAGs like this, and the idea we use to compute this F is to use recursion. So reduce it into smaller case of the same thing. And we do this by considering every possible next root layer. So the set of roots in R minus U. So we try every R prime like that. So we sum over these kind of things. And then we can use F in the smaller case, where R prime is the set of roots. And then again, account for the parent sets of these nodes in R prime. And this now gives us a recurrence to compute all the F values. If you do this, you get 4 to the n time preprocessing. But actually in 4 to the n time, you can preprocess things such that after that you can sample these DAGs in n squared time per sample. So we actually get polynomial time sampling. But this 4 to the n is quite big, so we actually have one idea to improve this. So it's kind of technical. I just give you a glimpse of how it works. So we simply modify the definition of F a bit by introducing inclusion-exclusion. So the first term, where x is equal to r, we just add something extra, which we have to subtract out, and so on. And this can now be written in terms of this function g, which is kind of a simplified version of f, which has only one argument, but still sums over DAGs. And G can actually be also computed recursively using inclusion-exclusion. So this thing, first computing all the G values and then the F values, can be implemented in 3 to the n time, after which we can do sampling in 2 to the n time. So actually sampling now becomes a bit slower. So we have like 2 competing algorithms. The first one has faster preprocessing time complexity, while the second one has better sampling time, actually polynomial sampling time. But this other algorithm has also the benefit that it's numerically much more stable. So you can implement it using only additional multiplication operations of non-negative numbers, which means that you can use just fixed size floating point numbers and the error will be negligible, which is not the case in the inclusion-exclusion. And also one thing you notice that we can only handle small n because these are exponential algorithms. And actually this 4 to the n thing is faster there because of what we ignore in the tilde or notation. So we implemented this algorithm and the implementation can handle like 17 elements or so. Okay, so now I'll switch to describing the other case where we assume this to be symmetric. So all the nodes are like the parent set weights only depend on the number of parents. So all the nodes are in a symmetric position. So this allows us to optimize the algorithm. So basically use the same algorithm as before, but we can optimize because we only care about the sizes of the sets. And we use this numerically stable algorithm because we want to account for the complexities of the numerical operations. So the adaptation will now look like this. So pretty similar, but we have to make some adaptations. And actually, if you want to do this monotonically, you have to eliminate this subtraction but like this. And a straightforward implementation of this now runs in roughly exactly n cubed time pre-processing, after which you can sample DAGs in n squared time. But this is not the end of the story, because actually we can optimize things, at least in the case where in the uniform sampling case, so where all the weights are 1. Because what happens there is that if you look at the root layering of such a DAG, all the root layers will almost always be very small. So what Kuipers and Moffat did with this observation is that they noticed that they can simply ignore a case where some root layer is larger than 20, because they have so small probability of happening. And for our algorithm, this would mean that we would simply set FRU to 0 if R is larger than 20, which would also allow us to truncate this sum into 20 terms. But this is not really enough for us, because we want exact sampling, and it's not okay if it cannot find all the DAGs. And also, we have a more general case of the symmetric case. So we have to adapt this a bit. So we define this number A, which is defined as the logarithm of the largest ratio between two parent set weights. So it tells us how far away we are from the uniform case. A is 0 in the uniform case, and it could be infinity in the general case, but usually something in between. And then we do all the computations using floating point numbers of log n bits. It's common to assume that we can do this in constant time, the numerical operations. And now we can actually see that if we set the limit on the root layer size L to order of square root n times a plus 1, then the probability that some root layer is larger than L is smaller than machine epsilon. So it's completely dominated by the numerical error. So we can use this limit. But of course we want to be exact, so we don't want any numerical error. So there we can use the standard trick of tracking error bounds of the numbers. And if in the sampling phase we don't have enough precision, we have to double the number of bits and do everything again. But this happens very rarely if we set things right. So actually we can control the time complexity. So we get that the pre-processing time is n squared times the minimum of a plus 1 and n. So in the case of uniform sampling, we actually get n squared, or closed uniform, we get n squared time pre-processing. Yeah, so that's it. Thank you.